Hello everyone, this is Dr. Sumit Chauhan and we are on the second layer, data link layer, and today we'll discuss a very important concept of error detection and correction. Now whenever we send the data from sender to receiver, there's a good probability or chances of having some disruption in between, and as a result the data gets corrupted or have some errors. Now, these are the learning objectives: to introduce the types of errors, to discuss different error detection methods, to discuss parity check, CRC, and checksum, to discuss different error detection methods. Now, data can be corrupted during transmission. For reliable communication, errors must be detected and corrected. Now, when the bits gets changed during the transmission from sender to the receiver, that is called an error. Now, error is of two types. We have single bit error and burst error. In a single bit error, only one bit in the data unit has changed. Now here you can see the data has been sent and the received data only has one bit that has been changed, and that's why it's called single bit error. Whereas a burst error means that two or more bits in the data unit have changed. Now this is basically an example of burst error of length 5. We actually take the length of bits from the starting bit error to the last bit error. Now the process of detecting the error at receiver end is called detection, error detection. And in error detection we have different methods. The first is redundancy, then you have parity check, cyclic redundancy check, and finally you have checksum. Error detection uses the concept of redundancy, which means adding extra bits for detecting errors at the destination. Now here we have some data at the right hand side, sender node, and then at the bottom at the sender node we have added some redundant bits to this data, so that with the help of these redundant bits we can identify or we can detect at the receiver's end whether the data that has been received is data error free or not. The three error detection methods are parity check, cyclic redundancy check, and checksum. We have a concept of even parity. So if we see at the sender node, we have a data 11000001. Then we calculate the parity bit. If you are calculating an even parity bit, then the number of ones in the data are odd right now is 3. To make that particular number as even, we add 1 to it. So the even parity bit would be 1, so that the number of ones in the total data including the parity bit should be even, and that's why it's called even parity concept. Error detection uses the concept of redundancy, which means adding extra bits for detecting errors at the destination. Now in parity check, a parity bit is added to the every data unit so that the total number of ones is even, since we have this as even parity bit. And if we are using odd parity bit, then in that case we'll try to make the number of ones as odd in the total data unit. Simple parity check can detect all single bit errors. It can detect burst errors only if the total number of bits errors in each data unit is odd. Now to overcome the disadvantage of parity check, that it can only detect odd numbers of errors, we have two-dimensional parity. So we'll make we add one extra bit horizontally and one extra bit vertically. In two-dimensional parity check, A block of bits is divided into rows and a redundant row of bits is added to the whole block. Now we have CRC, generator and checker, that is cyclic redundancy check. We add AND bits or AND zeros to the actual data, and then we have a divisor of n plus 1 bits, and then the remainder is called CRC, that is cyclic redundancy check. So when we send the data, we also send the remainder portion, that is CRC, along with the data as trailer. Now when the data and the trailer, that is CRC remainder, receives at the receiver end, it is again divided by divisor, and the remainder now should be 0. If 0 is there, it means that there is no error in the data, and if it's not there, it's non-zero, then you have to reject the data. Now in this binary division in a CRC, we have added certain zeros to the data, then we have divided with the divisor, and after dividing it with the divisor, we have a remainder, that is CRC at 001, and now we'll send the data, that is 100100, along with the CRC, that is 001. Now at the receiver end, when we again divide this, since we have the data as 100100 and 001 as the CRC, that is remainder at the sender side, that has been included with the data. Now we divide it again with the same divisor, and now you'll get 000 as a result, as a remainder. Then in that case, the data that has been received is error free. Now here we have a polynomial of degree 7. We have x raised to power 7, and that's why it's a degree 7 polynomial. A polynomial can be represented as a binary number, which is divisor. So this is how we can convert that 7-degree polynomial to a divisor. Now here we have certain standard polynomials that are used, something CRC8, CRC10, ITU16, ITU32. So we have certain polynomials that are fixed, that are standard, and these are the applications that where we use them, that is ATM header, ATM AL, SDLC and LANs. Now there is an example of checksum, that you have two sections, section 1 and section 2. Now if you have a checksum, all zeros, then we basically take sum of all those sections and then make a complement of it, and that complement of the sum is actually called checksum. Now we'll send AND bits along with the checksum, and at the receiver's end we again make a sum of all the bits including the checksum, and when we complement that particular sum, if the result is 0, then it means that the data is error free, otherwise we need to discard the data. Another method to showcase the same thing. The unit is divided into k sections, each of n bits. All sections are added using 1's complement to get the sum. The sum is complemented and becomes the checksum. The checksum is sent with the data. Now at the receiver's end, the unit is divided into k sections, each of n bits. All sections are added using 1's complement to get the sum. The sum is complemented. Now if the sum is 0, the data are accepted, otherwise rejected. Now to make it more clear, we have an example. Suppose the following block of 16 bits is to be sent using a checksum of 8 bits. So we have these block of 16 8 8, then we'll add these two numbers using 1's complement. So our sum would be 1 1 1 0 0 0 1 0. Then we'll make a complement of it, that is called checksum. So I'll replace 0 with 1 and 1 with 0. That would be the 1's complement. And the pattern that would be sent would be 1 0 1 0 1 0 0 1 0 0 1 1 1 0 0 1. Now the checksum 0 0 0 1 1 1 0 1. Sometimes there's a question arises that how many redundant bits should be added to the data so that we can try to, or we can able to detect the error at the receiver ends, and as well as not only the detection but the correction as well. So to calculate that how many bits should be redundant in a data, so the number of data bits, if they are m, then you have 1 2 3 4 5 6 7. Then the number of redundant bits would be m r, sorry. So the total bits that will be sent would be a combination of m plus r, or sum of m plus r, the number of data bits and number of redundant bits. Now since we are transferring the data in binary form, and binary has only two states, either 0 or 1, so we'll take that all those places where we have 2 raised to the power 0 or 2 raised to the power 1, 2 raised to the power 2, 2 raised to the power 3 and 2 raised to the power 4 and so on. So all those positions or locations are basically fixed for redundant data or redundant bits. At these locations we have the redundant bits, and at the rest of the locations we have the actual or original data. I'll talk about redundant bits calculation, R1. Now R1 will take care of all these bits locations, that is 1 3 5 7 9 11. R2 will take care of R2 3 6 7, and R4 will take care of 4 5 6 7, and then you have 8 will take care of 8. Now here we have the example for redundancy, that we have a data that 1001101. Now we have to send it and try to calculate the redundant bits. So redundant bit positions are 1 2 4 8. So to calculate at 1 3 5 7 9 and 11, these are the positions which are the part of R1. So we'll try to calculate or make number of ones at these positions as even. Similarly, talking about R2, then the positions are 2, 3, 6, 7, 10, 11, and at these positions the number of 1 should be even, so we'll put either 0 or 1 at R2. Similarly, for R4 you have the positions 4, 5, 6, 7, so the number of 1 should be even. We already have 2 ones at 6 and 7, so R4 would be 0. And similarly, finally R8, that is 8, 9, 10, 11. These are the positions. We already have 1 at 11 position. The number of ones is odd, so we add 1 at 8th position. And now you find that one bit has been corrupted, and that particular location is basically of the part of R1 as well as R2 and as well as R4. So in case if the data is the data bit, that the redundant bit at a particular location has detects that there is a data in its locations, then in that particular case we have 1, otherwise it's 0. So we'll find that R1, R2 and R3, that is 4, 2, 1. So we'll find that at the 7th position there is an error. So we'll replace or change that particular bit at position 7. Now burst error correction example is basically a data that we have data before being sent, then we have data in transition, and finally we have the received data. So the final conclusions: errors can be single or burst errors. Three common redundancy methods are parity check, CRC and checksum. Errors can be corrected by retransmission. Hamming code is the error correction through retransmission. Thanks for watching.